Hi folks, today we'll be talking about the reactivity series for elements. The reactivity series of elements give us valuable information about the relative reactivities of elements with respect to each other. The reactivity series have already been determined by scientists through experimentation. On the board you can see here is a part of the reactivity series for elements. We can't put all of them there because all the elements, we don't have enough space. As you can see here, lithium is ranked the most reactive element, followed by potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen, copper, and silver. In practical terms, this is what it means. That if I chose any one of these elements here, it means that all the elements above this particular says I choose aluminum, all the elements above aluminum will be more reactive than aluminum. But all the elements below aluminum will be less reactive than aluminum. Let's see how that can translate into something that's practical. Suppose we had an aqueous solution of zinc chloride, and we inserted into that a strip of magnesium. And we took it out and we observed the strip of magnesium, the part that was inserted into the zinc chloride. You will see a precipitate of zinc formed on the strip of the magnesium. That would happen because magnesium, being above zinc in the reactivity series, is more reactive than zinc and therefore was capable of displacing zinc from an aqueous solution of its salt. On the other hand now, if I took a solution of sodium chloride and I inserted an aluminum strip into that and absorbed it afterwards, you will not see any precipitate of sodium there, all because aluminum, being less reactive than sodium, was not capable of displacing sodium from the aqueous solution of its salt. So this is the reactivity series. If I choose any element, all those above that will be more reactive than down there, and all those beneath it will be less reactive than that one. So you can look at the reactivity series and you'll know which element is more reactive than the others and which is less reactive. Now, you see hydrogen, even though it's not a metal here, it's still placed in the reactivity series amongst the metal. Now, this means that any element above hydrogen in the reactivity series will be capable of displacing hydrogen from dilute solutions of strong acids. In this case, magnesium is reactive with hydrochloric acid. You will see hydrogen gas being displaced there. It'll come out in the form of bubbles. So that is it with respect to the reactivity series for metals. We also have a reactivity series for nonmetals. And this is how they've been ranked. Fluorine is ranked most reactive, followed by chlorine, followed by bromine, followed by oxygen, iodine, and sulfur. Same principle applies here. If I have an aqueous solution of any one of these here, and a bubbled fluorine gas through them, then fluorine will be able to displace any one of these. Same thing if we did it with chlorine will displace any one of these, and so on. So let us look at an example here of a single displacement reaction here. If I had a solution of potassium iodide, an aqueous solution of potassium iodide, let's have a slight yellowish in color, and a bubbled chlorine gas, which is a greenish yellow gas through the solution, I'll end up with the solution going dark. That is, because chlorine being more reactive than iodine, it will be able to displace the iodine from the solution of potassium iodide. And iodine will be produced, iodine being a dark solid, will make the entire solution go dark. Of course, it will precipitate on the influence of gravity. This has been simulated on page 98 of the text, And these ones here have been simulated on page 94 of your text. So this is the reactivity series of non-metals, and that there was the reactivity series for the metals. The next activity, this is what we're doing. We'll be looking at how we can formulate a mini reactivity series in the absence of any knowledge of the reactivity series of metals. So you'll be giving some metals, you'll be giving some aqueous solutions of their salts, and then we'll see how we can determine a mini reactivity series for those elements. Thank you so much. Let us suppose that we didn't know anything about the reactivity series, but we are given 4 metallic elements: magnesium, iron, copper, and silver. And we are asked to design an experiment to create a mini activity series. But we are also told that we can have aqueous solutions of their salts. Okay? So we have magnesium here, and we have magnesium sulfate, you have iron here, you have iron trichloride, you have copper here, copper 2 sulfate, and silver nitrate. How will you design an experiment to create this mini reactivity series? You can pause the video and you can think about that. Not you. Okay, but we still have to go on. This has been described on page 96 of the text. What we'll do is this. We'll take each of these elements here, okay, and we'll dip it into each of these separately and absorb. If a precipitate is formed on this metal here, it will tell us that this metal is more reactive than the one from which the salt is made. Okay, so we'll start the experiment by first of all introducing this magnesium strip into each of these and observe. Wherever a precipitate is formed, we have the table here. I'll put a check mark to indicate that this element here is more reactive than that one. So we first of all put this magnesium strip into magnesium and observe nothing happened. So we wipe that off clean, okay? Then we take this magnesium strip and insert it into the iron now. You see? We did get a precipitate of iron on this strip here, okay? We put a check mark against iron. Now we'll have to clean this out, or maybe we can break that off, insert it into the copper. Immediately, you see we get a deposit of copper on the strip. We make a check mark here against copper. And finally, we put it into the silver nitrate solution. And immediately you see we get a deposit there. So it means that magnesium is able to react with iron, copper, and silver there, okay? So put a check mark against silver. Now we'll use iron. Insert it into the magnesium. Wait for a few seconds there. Nothing happened. No check mark. You put it in iron itself. Of course, iron will not be able to displace its own self. Doesn't matter how long you put it there, you're not going to get anything. We clean it off. We now put iron into the copper and observe. Immediately we see a deposit of copper onto the nail there. We can clean it off, or we can use a different nail to put it into the silver now. Immediately you can see a deposit of silver on the iron nail. So we put a check mark against copper for iron and silver. Now we'll take the copper rod, put it into the magnesium for a few seconds. You see what happened? Nothing. Into the iron. No change. In the copper itself, you don't expect anything to happen. Copper will not be able to displace its own self. Nothing there. And then we take it and put it finally into the silver. And you can see immediately that you get a deposit of silver onto the copper. All right? Finally, so we take a check mark against silver for copper. Then you put silver there into magnesium sulfate, nothing. Into the iron, no change. Into copper sulfate, no change. Into itself, no change. So no check mark there. So I'm going to transfer the readings that I have here onto the board. How can we rank these? Which one do you think will be most reactive? Definitely one of the most check marks. So we can now say that magnesium here, we put at the top, is more reactive than the rest, followed by, of course, iron, followed by copper, and followed by silver. All right? So let's check our work here and see if what we did there was correct. Let's see if magnesium is above iron. Magnesium is here, iron is there, of course, it's above it. Is iron above copper? Iron, of course, is above copper there. And finally, is copper above silver? Yes, copper is more reactive than silver. So that's how we can create a mini reactivity series if you're given the elements and aqueous solutions of their salts. Thank you for listening. I hope that was useful. Sometimes we can also create a mini activity series by reacting those metals with the dilute solution of a strong acid such as hydrochloric acid. Zinc, for example, reacts with hydrochloric acid according to this equation here. So zinc reacts with hydrochloric acid to produce zinc chloride solution and hydrogen gas is liberated. If you do the ionic equation for the reaction, you'll end up with this. Zinc reacting with hydrochloric acid, hydrogen and chloride there, and get zinc ions. You break these down into their ions, chloride ions, and hydrogen. Remember, we do not break up solids and we do not break up molecules. So if you remove the spectator ions there, which are the chloride ions from both sides, we'll end up with a net ion equation as this, where zinc is reacting with hydrogen ions there to give you zinc ions and hydrogen gas being produced. Now we can break that up into what is called the half equations. Zinc ionizes like this, or we can say it oxidizes like this. That's all you're doing with your chemistry. It gets oxidized, they produce zinc ions, and 2 electrons are produced. The hydrogen ions now accept these 2 electrons. They accept those 2 electrons that are produced from the ionization of the zinc, and that is how hydrogen is formed. Okay? So this will be liberated from the solutions as bubbles. Now one thing I need to tell you, the only way that this gets liberated is if we provide electrons to these hydrogen ions here. And the electrons are coming from the zinc. And the rate at which this is liberated is dependent on the rate at which these electrons are produced by the zinc atoms so that they can be accepted by the hydrogen ions here. So, the rate of the liberation of hydrogen is dependent on the reactivity of that metal there. The more reactive the metal is, the faster it produces electrons, and the faster these ions they can collect the electrons to give you hydrogen. This is the information that I'll present my students with. Then they'll have to know to design an experiment. How would you go about creating a mini activity series? They'll do their own design. Then they'll tell me what the hypothesis, what materials they'll use. Write up for me a procedure, they'll make your observation, analyze the results, and then make a conclusion. In most cases, they're working groups, so they'll come up with their design. So they tell me they'll take equal masses of each of those metals in the same form, and they will react each with equal volume of hydrochloric acid of the same concentration and the same temperature, and they will absorb. Okay? So they'll have to write all of those things up for me, and then they'll do the reaction, We'll monitor the rate of the reaction by looking at the rate at which the hydrogen is liberated. So I have here for you just two of those metals. Focus a little bit there. Here we have granulated forms of zinc and magnesium. Okay, can you focus it a little bit more? So what we'll do, we'll react each with separately hydrochloric acid equivalent. So what the students will do, they have all of these and quickly they pour them into that together. So that's what we have. You can pour one after the other and you observe. Come. There. Now you can see here that magnesium is producing bubbles at a faster rate when compared to the zinc. All right? So in this case, if you have to make a comparison here of which is more reactive, we'll definitely say that magnesium is more reactive than zinc there. But we don't have all those other metals there, so we can't compare the rest. So what is going to happen, you're going to see different rates in which the gas is being liberated. And based on that observation, the students will rank the metals according to reactivity. Okay? So I hope that was useful. All right. Now, thank you for listening, and God bless.